Hi, in this lesson I want us to look in a bit more detail at Olympus Mons, the biggest volcano we know of, and look at a key feature uh, of its summit. For this lesson we're going to be working on pages 14 and 15 of your booklet, and you're going to need a scientific calculator and a ruler. Okay, let's go. When geologists look at an image or a map or a diagram, very often they're going to start uh, with this whole series of questions about what they're looking at. And a place like this, which is an image of the summit of Olympus Mons, does start to stimulate a lot of these questions. Now, when I look at this as a geologist, these are some of the things that are going through my head. How did these things form? How many of these craters are there? How old are they? What order did they form in? How big are they? Just as a start, really. And what I want to do is to get into answering perhaps some of these questions. So what do I see? When I look at this, I see a number of craters. Six in total. Now, each of these sort of cut across each other, and there's some interesting features in them. But let's start by trying to work out how big these craters actually are, just so we get some idea of size. We already know that Olympus Mons is huge, but how big are these? Now, when you look at your image of these, you can see that the crater, or the main crater at the top, isn't completely circular. We're going to put all these together as one, just to make it a bit easier. And what we have is roughly an oval shape. Now, to work out the area of an oval, what we need to do is we need to work out and measure, first of all, the diameter of the longest measurement you can take and the shortest one we can take. Let's call them D1 and D2. Once we've measured those and converted them to kilometres, so we find the average of these diameters by adding them together and dividing by 2. Then divide that by 2 because we want to work out the radius. Once we've got the radius, of course, we can work out the area by using the equation pi r squared. Okay. Now there are some other places on Earth where we can identify these odd circular or oval features as a result of volcanic activity. These are features called calderas. This is an example, a really spectacular one, from Antarctica, a place called Deception Island. This was, as you can see, a fairly steep volcano, and the middle part of it blew out and then collapsed in on itself, and it's just fallen below sea level, so the sea's been able to flood in to create the most incredible bay. There are other places on Earth where we see perhaps a closer link to it. This is the Santa Ana volcano in El Salvador. You can see craters here of different levels, created by different eruptions. We could apply the same techniques to this as we are to Olympus Mons. We can also try and work out the sequence that these craters formed in. Let me show you an example. There's a number of shapes I've drawn here, but we can work out which shape must have been drawn first and which one must have been drawn last, because of the way the shapes cut across each other. Let me try and demonstrate how I drew these. So the first shape I drew was the circle. The triangle came after that, and we know it must have come after that because the shape of the triangle cuts across the circle. The youngest, or the most recent shape, is the square, because that cuts across the other shapes that are there. So we could put these shapes in order. Circle for oldest, then the triangle, and then the youngest is the square. It's what geologists call the law of cross-cutting relationships. Can you apply that to these craters? Which of these craters do you think must be the oldest one? Which must be the youngest one? Are there any that we can't quite work out? Okay, it's time to press pause and have a go at the questions on page 15. See what you can come up with. Okay then, let's see what we've come up with. It's time to press play. When I measured these craters, I measured D1 to be about 93 kilometres and D2 to be about 80 kilometres. So if I work out the average of those, get 86.5, divide that by 2, I end up with 43.3 kilometres as the average radius of these craters. To work out the area then, I use pi r squared. So it's pi times 43.3 squared, which gives an area of these craters of 5,880 square kilometres. Just to put that into perspective, that's over a quarter of the size of Wales. And that's just the craters, remember. So, I also asked you to think about how these form. These are certainly volcanic craters. We can see the features labelled X on your map. Those are cracks that have formed as the magma chamber is emptied, as this crater has fallen in on itself to form this feature we call a caldera. You'll also notice that there's none of the other features we'd expect to find of an impact crater. There's no debris that's been thrown out. There's no central point where a bit in the middle has risen up again. These are definitely volcanic. We can also work out the order in which they formed. 2 is the oldest, 4 and 6 come after that, but before 3 and 5, and then 1 somewhere after 2, although we don't know exactly where that crater 1 would have formed, because it only cuts across crater 2, so all we can tell is it's younger than crater 2. Did you manage to come up with something similar? There are a lot of questions, though, we could still ask. What else have you come up with? What else would you want to know about this place? What else perhaps could you go and find out? And can we compare this to anywhere here on Earth? So, as we see the sunset on Olympus Mons, it's worth pondering for a moment. We can apply the same ideas that we use to interpret geology here on Earth to the geology we see on Mars. Even though no one's been there, no robot has been there, we can still work out an awful lot just by careful observation. but there's still so much to find out. I think it's an amazing topic for us to study. So we're going to get into this in far more detail when we work on theme 2, sometime next term. Okay, that's enough for this lesson. I'll see you next time.